Alright, everything should be set up now, so welcome to the MathSoc MATH2011 and 2111 stream. So this is just a revision seminar, hopefully you guys should know this, and we're just going to go through some content related to both of these. So my name is Jason and I'll be presenting the first half today, and Lockie will be presenting later on after me. So for today, well, in general, there are these 8 topics which we're going through. We're going to go through, I'm going to go through topic 1 and 2 today, and then Lockie will go through, I believe, topic 3 and 4. And then the second MathSoc 2111 and 2011 seminar will be on Friday, so that's for the second half. So I guess I'll just get started. And we're going to first look at topic 1, which is curves and surfaces. And I guess just before we get into actually a lot of the content that I'm going to cover today in terms of the theory, it's a lot of definitions. So we are just going to skim through most of them and try some practice questions. Hopefully you guys do know the definition. If there are any questions regarding to them, just send it through in the chat, and there should be people monitoring the chat, and they will answer those questions. Alright, so we'll just get started. Topic 1, curves and surfaces. Firstly, let's look at a couple of definitions. And the parameterization of a curve in Rn is just written like this. So it goes from I to Rn, where I is just some interval on R. And I guess by convention, you usually use A and B for the 2 endpoints, and it goes to Rn. We'll look through other definitions. So multipoint is a point through which the curve passes more than once. For example, if we have a curve that starts at A, ends at B, and goes like this, the intersection there will be a multipoint. So we just went through that point more than once. Also, A and B are called endpoints. So, sorry, this should actually be C of A and C of B. So C of A and C of B are the endpoints of the line. And if C of A equals to C of B, so it starts and ends at the same point, then we say the curve is closed. So this stuff should be pretty easy, just some definitions that we're going through. Next is just defining some limits and what the derivative is in multi-dimensions. So the limit, it is kind of self-explanatory. So the limit of a curve, so if you limit t to a, c of t, it's essentially the same thing as each component of the curve being limited to that value as well. And that's what we have here. So it's the same as component 1 being limited for t to a, same for all the way up to the end component. And derivative, same kind of vein, where the derivative of a curve is just the derivative of each component of it. I guess what's more interesting is how we can interpret this and what we can make out of it. The first derivative, so c dash of t, it's the tangent vector, and it's also the velocity at t. And this is if, so it's the velocity at t if c of t gives you the position. So people that do physics should know this, and I guess based on first year maths as well. And similar, in a similar sense, the second derivative gives you the acceleration. Alright. Also, I guess there's three different ways we can represent a curve. So you guys should be comfortable with this as well. So there's a graph implicitly as well as parametrically. Alright, we'll finally move on to a question now. So this first question here, what we have is, suppose we have this surface S, and it's given by this equation here. So x squared plus 3y squared minus z squared equals to 1. We want to sketch the intersection of S with the xy as well as the xz as well as the xy plane. And then we just needed to identify any inset and asymptote as well and name it. Wait, sorry, I feel like there's an issue with the audio. Give me a second to try to fix that. Alright, sorry, does this sound better? Alright, well, I'm not too sure if the audio is fixed, but I'll just keep going. Let me know if it gets too bad. But continuing with this question, so we want to sketch the intersection of S with the xy and the xz plane. Firstly, let's actually see what S looks like. I guess, sorry, give me one sec. Alright. I think we're just going to keep going. Sorry for the delay. But continuing with this question, we just need a graph on the x, y, and xz plane. First, let's just look at a S and see what it looks like. It's in the exam, it's very hard to actually picture what this would look like. But just to give a better idea, it does look something like this. So this is the actual graph of S, which is x squared plus 3y squared minus z squared equals to 1. And what we want to do is restrict it to the xz plane first. So if we restrict it to the xz plane, this essentially means that y is equal to 0. So we limit y to 0, and then our new equation just becomes x squared plus 3 0 squared plus z squared equals to 1. Negative here. And our equation is x squared minus z squared equals to 1. So you guys should be familiar with what this actually is, and this is a graph of a hyperbola. And it would just have asymptotes at, if we have the zx plane, z equals x, z equals negative x, and our hyperbolas will just look like such. And the intercepts are 1 and negative 1. Alright, so this is the intersection with the xz plane. Now let's look at the intersection with the xy plane. So for the intersection of xy plane, similar idea. This is when z is equal to 0 now. So what we will have is x squared plus 3y squared minus 0 squared equals to 1. So x squared plus 3y squared equals to 1. Once again, this should be something that you guys are familiar with from first year, and it will just be an ellipse, which intersects at 1, negative 1, as well as 1 over root 3, and 1 over negative root 3. This is the xy plane, and this is an ellipse. And this one here is a hyperbola. Alright, so that should be the answer to this question. Also, I am doing working out here, but on the slides there is just the answers as well. I think I forgot to mention this earlier, but we will release the slides, so if you guys want like typed up solutions, you can just refer back to the slides. Alright, so that's this question here. And that's actually the end of topic 1, so nice and short. Move on to topic 2, which is probably the harder one out of the 2 topics. And for topic 2, it's just point set topology. Same as what we were going to do earlier, we're going to go through a couple of definitions as well as some theorems, and then have a go at some questions. So first is the idea of a ball. So the definition of a ball is given here, and it's defined as the set around A, such that the distance from x to A is less than epsilon. What that looks like in 1D is, imagine if we have A here, let me make that a bit more. That round bracket there will be our ball. So any points within here is inside the ball of A. In 2D and usually in high dimensions, we just represent it as a circle rather than a full ball. So if we have point A here, this distance is epsilon, then any point in this here is the ball of A, the ball centered around A of radius epsilon. Punctured ball is essentially the exact same thing. The only difference, however, is just that the point A itself is not included, so it's an open circle for the punctured ball. which kind of makes logical sense, and it's given by this. So that last inequality there gives us A is not included. All right, so that's a ball. An open and closed set, which is the next section here. Once again, a lot of definitions, and hopefully you guys do remember this stuff. So we'll kind of skim through it. First one is interior point. Just say we have some omega. This set is omega. An interior point is just any point inside here where you can construct a ball around it, such that every value in that ball is contained within omega. If we look, so that point x is part of omega. If we look at this point here, just call it A, and draw a ball around A, we can see that some of the points inside that ball of A, no matter how small you make epsilon, no matter how small, some of the points are outside of omega, but on the other hand, some of the points are inside omega. And what we call A is a boundary point. And I guess this here is the formal definition of a boundary point. And I guess for an open set, so open set is when every point is an interior point. Omega is closed if the complement is open. And I guess the theorem here is just that, firstly, a union or intersection of an open set is open. So if we have omega and, I don't know, some other set A, and they're both open, the union and the intersection of them are also open. And the same as for closed sets. Alright, so those are the definitions. Once again, we're going to go to an example now. So for this question, it says use the definition to show that the set from -3 to 1 is not open. So if we think back to what we said earlier, a set is open given this definition. So for any x naught, which is an element of the set, there exists an epsilon larger than 0, such that the ball centered around x naught with a radius of radius of epsilon is included in omega. So it's a subset of omega. For this question, we want to prove the opposite. So we want to prove the opposite. And what that means is that we can find it at x. So there exists an x naught, which is inside omega, such that for any epsilon we choose larger than 0, there exists a ball around epsilon, which is not included in omega. I guess this can be seen if we were to do this graphically. Let's draw this. So sets from -3 to 1. What this looks like on the number line is like such, and it goes from -3 to 1. We can see that if we choose our x to equal to -3, no matter how small an epsilon we choose, just say some epsilon like that, and then this gives our ball, anything to the left of this point here is actually not included in the set. So anything to the left of -3 in that little ball that we drew is not included in the set omega. I guess that's just a graphical representation. How we can do this a bit more mathematically rigid is, so let's choose x naught equal to -3. Then what we see for all epsilon larger than 0, we get y naught equals to x naught minus epsilon on 2. And then we see this should be an element within the ball surrounding x naught to epsilon. Once again, graphically, what we're doing is looking back up to the number line, we're choosing y to be here. So that's y naught. And we can see that's clearly inside the ball surrounding x. And then how else we can write y is y naught is equal to -3 minus epsilon over 2. And we can see that this is clearly less than -3. Therefore, y naught is not an element in -3 to 1. Thus, if x naught equals to -3, the ball of x naught around epsilon is not a subset of -3 to 1. And this leads to, so thus if x naught's that, then we get that the set -3 to 1 is not open. Alright, so that's the answer to this question. So essentially what we need to do is just show that there exists a point such that the ball around that point is not included in the set, and that will show that it is not an open set. Alright, so we'll move on to the next section now. And then here's just the typed up solutions, which, as we said, if you find it online, you can just look through the solutions here. Alright, the next part we're going to look at is the limit of sequences. So what the limit of a sequence is, by definition, if we have a sequence like such, and what that essentially means is it goes from x1, x2, all the way down to infinity, I guess. So the limit of this sequence, so x here is the limit of the sequence, if and only if, for all epsilon larger than 0, there exists a natural number such that we can choose a k larger than n, and that is inside the ball of x around epsilon. That sounds like just a lot of like mathy terms. So to draw this graphically, just say we have some x here. Just say we have some x here, and we have some sequence. So just say x1 starts here, x2 goes here, and so on and so forth, for all the way up to a certain value. It just keeps spiraling inwards around x. What we can say is, if we were to construct a ball around x here, we see that any value within the sequence, so these ones that I highlight, all these values are inside the ball around x. So this is then a limit to the sequence. So x will be a limit to whatever sequence I just drew there. That's what it means in terms of a visual representation. And yeah, once again, we just have a bit more definitions here. It does lead pretty easily from the definition. So looking at the next section, here we're going to look at the interior and boundary. And this is more just, once again, notation. So the interior of omega is a set of all interior points, and the boundary of omega is the set of all boundary points of omega. And that's denoted by this. Finally, the closure, which is denoted like such, is the union of the interior points with the boundaries. We have a couple lemmas here which you can read through, and they essentially just go through limit points, interior points, and boundary points. Alright, we're now going to look at a definition here, so the limit of a function. You guys would have looked at limits of functions in first year, but that was only in 2 dimensions. Now we're going to stretch this limit out to infinite or multi-dimensions now, so n dimensions. Essentially what it is, here's the formal definition, and what it is for epsilon larger than 0, there's this delta such that if x is an element, so for all x inside our set, x is an element around the ball of A intersect the set, then f is an element of the ball around B. Just looking at it, it seems, once again, like a lot of massey notation. What this actually means in terms of a graph is, imagine if we have f of x and x, and we have some graph that looks like this. We have a point, just say A here, and point A correlates to B here. Let me copy the definition down. Alright, so what it's saying is essentially if x is an element of a ball around A, so just say we have some ball around A like that, then if it's inside this ball, then we can find a ball around f of x such that, a ball around B such as f of x is an element of it. So if we construct a ball around B, so let's say this leads up to here, we can construct a ball around B like this, such that, we construct a ball around B like this, such that f of x is an element of that ball. That's essentially what the definition means. Yeah. And now we're going to look at some useful theorems related to it. This stuff is pretty, once again, self-explanatory, and some of this does lead on from one variable calculus. So first one is the limit of x to A for f of x is equal to B if and only if that each component's limits to B, each component of B. That makes sense. So it's essentially saying that if limit x to A equals to B, then f of I of x, limit this x to AI, or A, is equal to, I guess, B of I. So let me draw this out. So F1 is B1, B2, all the way up to Bm. Same thing here. So limit x to A of f of m of x. So essentially saying that these two are equivalent. So yeah, essentially saying that each component of f approaches each component of b. The next one here is saying that if the limit of x of a to f of x equals to b, then for every sequence, the limit of that sequence would equal to a, then f of a is also equal to b. That's a useful one that we'll come back to later. We'll see how to use it in one of the questions. The next part is kind of the part that I said should be quite common knowledge by now, and it's something that you would have seen in high school maths. So it's essentially that the limits add together, add two limits together should be adding of a and b, same as multiply and same as divide. I'm just going to skim through that. Hopefully you guys are comfortable with that. All right. The next theorem is also a very useful one, which is the pinching theorem. And once again, this does extend from first year maths. And this pinching theorem essentially says if you have three functions, g of s, f of x, and h of x, and g of x is less than or equal to f of x, which is less than or equal to h of x, if you limit them to a point where g of x is equal to h of x, which equals to b, then f of x would also equal to b. How you can kind of imagine this is if you have a graph like this, where something like this is f of x, this here will be h of x, this here is g of x. We see here that the relationship holds that g of x is less than f of x, which is less than h of x. So if g of x, just say approaches some value b, same as h of x approaches some value b, it's essentially, you can think of h of x and g of x like this, pinching together. So that's why it's called the pinching theorem. And sandwiched in between the two is f of x. So f of x must also approach b. So that's essentially the pinching theorem here. Very similar to the single variable calculus, just in multi-dimensions now. All right, we'll finally move on to a question. And this question here is, show that the following limit does not exist, where x plus y over absolute value of x plus absolute value of y, and you limit xy to 0, 0. Earlier, I did say we'll come back to a theorem which is pretty important, and that's this here. So this theorem here, where the limit only exists when, if you have a sequence, every sequence must approach the same value. So I guess our strategy here is we want to show that the limit does not exist. So we can find two sequences which leads both to 0, 0, and f of the sequence doesn't equal to the same thing. Then we can say the limit doesn't exist for this particular function. How we're going to do this is, let's define a sequence first. So let's let x of k equal to 1 over k, and then y of k equals to 0. So what we have is 1 over k naught, and when you limit k to infinity, clearly this becomes 0, 0. So we have a sequence which limits to 0, 0. And now let's see what f of k is equal to. So f of k, when you limit k to infinity, I guess I should define f of x to be, so f of x equals to whatever we have up here. Alright, so let's find what this limit is now. And subbing in 1 over k plus 0 over 1 over k plus the absolute value of that plus the absolute value of 0. We get that this should just equal to 1 because, well, we should also define k to be an element of the positive integers. So 1 over k here is always positive. So that just cancels out to become 1. Alright, so this is half the work done. We found one sequence where the limit leads to 0, 0, and f of that sequence is 1. Now let's define x of k to equal to negative 1 over k, y of k equals 0. Once again, if you limit k to infinity of 1 over negative k and 0, this is also equal to 0, 0, and similarly, k is a positive integer. So if we limit k to infinity of f of this new sequence, that's equal to negative 1 over k plus 0 over the absolute value of negative 1 over k plus the absolute value of 0, which is negative 1 over k over 1 over k, which is negative 1. Alright, so now what we see is that these two sequences produces different results for f of that sequence, and then therefore the limit cannot exist or does not exist for 0, 0. Alright, that's this question here. Moving on to the next question. Now, once again, the solutions, which you can find later. Earlier, we proved the case where the limit doesn't exist. Now we'll show that the limit is 0. So the limit does exist in this case. There's lots of different ways to approach these questions. And for this way, what I'm going to use is the pinching theorem. So we use the pinching theorem. And just a quick refresher on the pinching theorem. If we have three functions, g of x, which is less than or equal to f of x, less than or equal to h of x, then if limit x to a of g of x equals to b, which also equals to the limit of x to a of h of x, if that's true, then as x approaches a of f of x is also equal to b. Clearly, we do need to use the hint they gave us, so we need to use this hint somehow. And if you compare the two, actually, the function that they give and the hint that they give, they are very similar. The only difference is this x versus x squared. And I guess that's kind of a major giveaway of what we should do. We should multiply both sides by x, and that will give us the function. Alright, so let's do what we said. So we have this here. If we multiply both sides of this by absolute value of x, then what we get is absolute value of x squared of y over x squared minus xy plus y squared is less than or equal to x, absolute value of x. And this is actually really all we need. If we show that this approaches 0, so if you limit xy to 0, 0 of this function, and you limit this also to 0, 0. What we get is that the right-hand side just equals to 0. Therefore, this thing here is also equal to 0. And finally, our final function is also equal to 0. I guess what might seem a bit strange here is that we seem to only have two functions, right? So, or just one inequality there. But in the pinching theorem, it looks like there's three. So I guess it kind of does seem strange that we were able to just go like, oh, from the pinching theorem to this, and then to get our answer. But what's actually going on is that implicitly there is three functions. So if we were to write this out fully, let me add an extra page. If we are to write what we have up there implicitly, this is the same thing as doing x squared over y. X squared minus xy plus y squared is less than or equal to x, and larger than or equal to negative x. And that's kind of how we get the pinching theorem. So if you limit both sides, the left and the right side, to 0, then it's 0 equals to that equals to 0. Alright, that's question 3 that we just went through. We'll move on to the next section now, looking at more definitions. And then for this one, continuity, continuity is the same thing as what you'll expect in single variable calculus. Essentially, it's an extension of the limit. So if the limit exists at that point and it's equal to the value of the graph, then it's continuous at that point. And for f to be continuous on a whole set, omega, so it's continuous on its domain if it is continuous at every single point inside of it. That's what continuous means. So we'll skim through that and look at the pre-image now. So the pre-image is pretty similar to just like an inverse function, and it's defined to be the set here such that the pre-image of the set U is the same as the elements of where f of y is in U. So as I said, you can think of pre-image as similar to inverse functions. I guess the only thing here, to be more precise, it should be an inverse relation, because it's not, the pre-image is not always a function, so it doesn't map one-to-one. It can map to many different values. Alright, so here are some theorems as well. So first one is, if f is continuous on omega, so if f is continuous on omega, if and only if U is open, then, so this theorem is, if U is open in Rn, then the inverse is also open in Rn now. And then the next theorem is, suppose that omega is open, f of a is an interior point of f omega, and it's included in the ball, then a is an interior point of the inverse that ball. So that's kind of some definitions and theorems. Once again, we'll move on to the example now. So this example here is, first let's find the pre-image f inverse of 1. So if we think back to the definition of the pre-image is the set of y elements of Rn such that f of y is an element of U. In this case here, U would be the set 1, and we want to find this essentially the set of xy. So what we want to find is f of xy such that f of x of y is equal to 1. That is the goal here. And what this set should just be, based on our definition of the function, we see that for here, f of xy is equal to 1 if x squared plus y squared is larger than or equal to 1. So what that essentially means is the pre-image is equal to the set of xy such that f of xy is an element of such that x squared plus y squared is larger than or equal to 1. And this here would be our pre-image. Alright, part B just says plot the pre-image and identify known curves. We just shuffle this across a little so we have a bit of space to graph it. So we want to plot this graph, and we should know that that's just a circle, a unit circle actually, with the exterior here shaded. And just identifying the curve is a unit circle centered at origin. Okay, that's the question about pre-image. And I guess this will be our last session for today. So we're going to look at a bit more theory and finally go to the last practice question. In this section here, once again, looking at some definitions. Firstly is what it means to be bounded. And a bounded set is essentially if you can choose a value m such that the distance from the origin to any value x in the set is less than or equal to that m. For example, if we have this as our set, here is the origin, and if we define m to be this value here, whatever distance that is, that's m, we see that from the center to any x point inside that blue circle, the distance is always less than or equal to that capital M. So this is a bounded set. An example of when it's not bounded is if we have like some graph, can't really see that. If you have some graph like this that goes up to infinity, from now, if we choose the origin to no matter what m we choose, we can't enclose all of the values of this hyperbola because it just tends to infinity. So this here is not bounded. Compact is if it's both closed and bounded. And the theory that leads to that is assume K is a subset of omega and K is compact. then f of k is also compact. And omega is the domain that f maps from. Another way of saying this is just that a continuous function, a continuous function, if you apply a continuous function on a compact set, it is still compact. Alright, moving on to path connected. Path connected sounds basically like what the definition is basically what the name of it sounds like. It essentially is, if you have 2 points x and y, choose a different color. So some set here, you have point x, point y. If we're able to draw a continuous line from x to y, then it is path connected. By, standard notation, they want to represent it in a parametric form, where you have t from 0 to 1, and the beginning of the curve is x, and the end of the curve is y. It's pretty self-explanatory what this theorem means. An example of a set which isn't path connected. So imagine these two circles are both part of omega. Then clearly x and y cannot be joined by a path such that every single point along this path is inside omega, so it's not path connected anymore. Similar to what we saw earlier, the next theorem is that if B is path connected, then f of B is also path connected. Alright, so that's kind of the theory here. We'll move on to the practice question. So this practice question, first thing you want to do is use the definition to prove that the unit square is bounded. And just a reminder, bounded essentially means that the distance from any element inside X can be less than or equal to M, where M is just some value we select. Alright, let's have a go at part A first. So if we were to draw a diagram of S, it will become pretty clear why this set is actually bounded. So it maps from R and theta are our variables, and our bounds, our thing here is just a unit square. So it looks something like this, where here's 1 and here's 1. And S is all of this. Clearly it is bounded, and the max distance is actually this here. And that distance there is just root 2, and you can clearly see that using Pythag. So what we can do, we choose M to equal to 2. Or you can pick any number. It can be 2, it can be root 2, it can be like root 3, just any number larger than or equal to root 2. And what we get is the maximum distance from X is equal to root 2, where X is an element of the set. And then therefore, we get this relation here. And we see S is bounded. Alright, let's look at part B now. So part B is use the definition to prove that the unit square is path connected. Alright, so if we think back to the definition, let's copy all this across. So if we can make a continuous function that goes from x to y, and all of it is inside omega, then the set omega is path connected. So what we need to do is let's choose two arbitrary points, x, which equals to r1, theta 1, and this will be x1. Let's just do it as x, and then y is equal to r2, theta 2. Since this is part of our set S, what we know is that R1 is in between 0 and 1, and same as theta 1 is between 0 and 1. Same thing for the other side. So R2 is between 0 and 1, and so is theta 2. If we're going to create a continuous function, we can easily do a line function, which is probably the easiest thing to do. So if we define the function of t to equal to 1 minus t of y plus, 1 minus t of x plus t of y, clearly it starts from x and then ends at y, equals to y. Now we just need to prove that every single point along this line also lies within our set S. To do this, what we can do is multiply this by 1 minus t, multiply this by 1 minus t, multiply this by t, multiply this by t. So what we get here is that 0, 1 minus t, less than equal to 1 minus t. And then I'll write it out for every other one, but it's the same idea. Now, let's add these two inequalities, 1 and 2. So if we add the 2, what we get is 0 is less than equal to 1 minus t of r1 plus t. So less than equal to 1. And if we add 3 and 4, what we get is basically the same thing. So I'm just going to speed through this. Alright, so now we have these two inequalities. Hopefully everyone sees where we're going here, but essentially these two inequalities is what actually defines our function here. So if we were to rewrite this function, it is 1 minus t times x, which is r1 theta 1, plus t r2 theta 2. And hopefully you can see that this here and this here, this will be the, the first component of our function, and this here is the second component of our function. And then this then leads us to, therefore, this here is completely within our set S. by definition, S is path connected. Alright, that's part B of this question. Looking at part C now. Part C is you want to find the image of S, where image of f of S, where f equals to this function here. Alright, so let's paste this down here. We want to find the image of this, and just remember S was the unit square. Alright, so when you look at f, hopefully that rings a bell that this is just, well, it's very similar to polar coordinates, and actually just is. So it should remind you of polar coordinates. And I guess intuitively that just means it should become a circle. So let's just prove this mathematically. If we have x equals to r cosine pi theta over 2, and y equals to r sine pi theta over 2, x squared plus y squared equals to r squared. So you can see here that clearly x squared plus y squared is r squared. So what this maps to, it's actually a unit, or it's a circle with radius r. The other thing you should remember is that r is bounded between 0 and 1. So this actually just maps to the inside of the unit circle. So far we have this as the inside of unit circle. Now the next thing to look at is theta also has a limit where it's in between 0 and 1. That means pi theta over 2 is also bounded between 0 and pi on 2. So our image is now then, it limits to the first quadrant of the unit circle. So if we were to draw this up, it would look something along these lines, from 1 to 1, and the interior here. And finally, the last part is f of s path connected? Just by inspection, so if we look at this here is f of s. By inspection, it does look path connected. So if we just choose any 2 points, we can clearly draw a line between the two. So we should know, just intuitively, it is path connected. How we can prove that is by one of the theorems we looked at earlier. So let me just copy the theorem down. So it says here that if B is path connected, then f of B is also path connected. And then what we showed earlier is S is path connected. Therefore, f of S is also path connected. So yeah, simply by this theorem, f of S is path connected. You can go through like the complicated process of constructing like a continuous function which shows it is path connected. So just going by the definition. That would end up working, but it is a lot more complicated. So using this theorem would be a bit easier. Alright, so that actually brings me to the end of my section here. You can have a look through the solutions of question 5 as always, as all the other questions. And yeah, the next section is differentiable functions. So as I said, this is the end of my section. It was nice meeting you all, and I'll just pass it on to Lockie, who would continue the rest.
All right. Thank you a lot to Jason for presenting the previous sections. Now I'll be moving on to the next two sections, which are differentiable functions and integration. So we're going to get started off with looking at partial derivatives. Okay, so partial derivatives are a way of extending the normal derivative from R to R to functions with multiple variables. Essentially, what we're going to be doing is looking at the rate of change of the function with respect to a certain coordinate axis. So, for example, in this definition here, what we're working with is EI. Now, that is the standard basis vector in the ith direction. So that corresponds to the coordinate xi. We could easily find the partial derivative with respect to the x-axis, for example, by using this. So that would just be equal to the limit as h goes to 0 of f of a plus h times the I vector minus f of a divided by h. So you can see that this definition here is very similar to what it looks like for just functions from R to R. It's sort of extending it onto functions of multiple variables. Now, when we work with, I guess, looking at the derivative of a function of multiple variables, it's not just sufficient to look at the partial derivatives. So there is something called a Jacobian matrix, which encodes all the information about all the partial derivatives into one mathematical entity, which is the Jacobian matrix. So you can see that as you go along each row, what you're doing is keeping the same component function. So in this example, we can think of the function f as consisting of f1, f2, all the fm component functions. And as you go along a row, you remain along one component function, but then look at the partial derivatives for the coordinates x1, x2 up to xn. Now, as you go down each column, what you're going to be doing is changing the component function, but keeping the same coordinate that you're differentiating with respect to. Now, we have a theorem here that says that if we're working with an interior point and some function from Rn to Rm, now, if f is differentiable at some point A, then all the partial derivatives exist at A, and furthermore, the derivative of f at A, so this is the derivative is equal to the Jacobian matrix at A. Okay, so that makes our Jacobian matrix very powerful because assuming these conditions hold, that is the derivative of the function. But now we have to talk about what exactly is the derivative, and that brings us into a discussion about affine maps. So an affine map is just some function that consists of a linear component. So this is a linear map. Remember from first year that a linear map is one that preserves linear combinations. So this would be equal to lambda L of x plus mu L of y. Okay. Now we also add on top of that some point y naught. So the idea here is that a function has an affine approximation if this limit equals 0. So the question is, what is an affine approximation? Well, with respect to just single variable calculus, the affine approximation is a linear approximation. When I say linear here, I'm referring to the graph of a line. But when we work up to, say, functions from R2 to R, what we're going to be doing is looking at the tangent plane to a graph. So really, the reason why we introduced this idea of an affine approximation is this condition here. A function f is said to be differentiable at a point A if f has an affine approximation at A. So what we need is for there to exist some affine approximation Specifically, the condition for differentiability can be reworded like this. A function from Rn to Rm is differentiable at a point A if and only if this condition is true. Okay? So it's important that it is this condition that we're looking at when it comes to proving differentiability. It is not the fact that partial derivatives exist. Okay? It needs to be the fact that this limit goes to 0. Just because partial derivatives exist doesn't necessarily mean that the function is differentiable. So we need to be checking this limit and proving that it's equal to 0 to show that it's differentiable at A. And really what this limit is telling you is that the function is well approximated by this particular affine approximation. So this is the affine approximation we're looking at. And you can see that's written in terms of the Jacobian matrix, which in this case will be referring to the actual derivative of the function. So now let's move this information into a question and see how we can apply this. So let's consider some function, piecewise function, defined as so. So what we have is it's defined like this when we're working with everything that's non-zero, and then it's equal to 0 at the point 0, 0. So now find all the partial derivatives, df dx and df dy at the point 0, 0. So to find these partial derivatives, well, in general, partial derivatives are quite easy to find because we can just use the rules that we learned in single variable calculus. However, in a case like this, when we're looking at the point 0, 0, we will have to apply the definition and we can't just use our rules for differentiation. So what we need to do is we need to use the definition. So let's just look at df dx, for example. How do we find this from the definition? Well, the definition can be written like this. That is f of 0 plus h, comma 0, minus f of 0, 0 divided by h. So you can see in our definition all the way up to here with partial derivatives, it's f of a plus h ei minus f of a. Well, in this case, we won't be working with vectors, but instead just looking at the coordinates, you can see that this x-coordinate is going to be 0 plus h, and the y-coordinate is going to be 0. And we subtract f of 0, 0. So that's what we're going to be looking for. We need to find this limit. And well, you can see that this sort of simplifies nicely to this expression. So f of h, and we know f of 0, 0 is actually just 0 because that's how it's been defined, and divided by h. So now f of h, that should be f of h0 divided by h. Well, that's just equivalent to substituting x equals h and y equals 0 into this expression up here. So you can see that because h is non-zero, that's why we have to use this. So when we substitute it in, what we get is this expression here, and after simplifying, what we should get is this here. Now, we need to show that this limit equals 0, and what we can do is actually apply the squeeze theorem as Jason was talking about. So that is pinching theorem, squeeze theorem, same thing. Now, to actually apply that, well, you can see that sine of 1 on h squared, its absolute value is less than or equal to 1. Okay, so by multiplying by an h here, we are looking at this now expression. Now you can see that as h tends to 0, it would make sense that the middle term here, so the middle part of this, would also tend to 0. That's where we get the limit from. Now the question, if you're doing this in the exam, what you want to be doing is wording this a bit better than I have. So clearly outlining the squeeze theorem. So you can't just say equals to 0 by squeeze theorem, pinching theorem. You actually need to fully prove it, so by actually exploring these inequalities. Now, we've then found df by dx at the point 0, 0, and we showed that that's just equal to 0. What about df by dy? Well, we can do a very similar process. You can see that instead of doing f of 0 plus h 0, we're going to be doing f of 0, comma 0 plus h. That means we substitute x equals 0, y equals h in, and we'll get a slightly different but very similar expression, which we can also apply the squeeze theorem result to. Okay, that equals 0. So we've shown that both of the partial derivatives at the point 0, 0 are 0. Okay, so we found both of them to equal 0. Now the next part of this question is to prove that f is differentiable at the point 0, 0. So remember what I said, we can't just use the fact that partial derivatives exist to show that it's differentiable at 0.00. What we actually have to do is use the definition, the affine map definition, to prove that it's equal to 0. So specifically, we need to show this is true. So this is a big thing, so let's break it down. So we need to show that this is true. This is the exact same as our original definition here. But what I've sort of done is use the fact that the point A is 0, 0, and the point X, or the vector X, is XY, and sort of sub that in. Okay, and now we get this, and we need to prove this equals 0. So how do we tackle that? Well, we can notice that the Jacobian matrix at the point 0, 0 is actually just df dx df dy equals 0, 0. Okay, so what we get is the 0 matrix, which means that this whole expression here, all of this should become 0. Okay. Furthermore, f of 0, 0 equals 0. And also this thing here should just equal to the length of just xy vector. Okay. So we can see that what we're going to be getting is actually this expression here. So what I've sort of done is just use the fact that equals 0, that equals 0, that just equals xy, and this thing here is going to be x squared plus y squared sine of 1 on x squared plus y to the 4th, because obviously in this case we're dealing with non-zero xy and we're tending them to 0, so we can use that. Now notice that this part here, this sort of length of the vector xy, is just the length of a vector, so that's the square root of x squared plus y squared. That's what we normally work with. Now what we can do is look at our expression here, and it can actually be simplified further, just by using the fact that we have x squared plus y squared on the square root of x squared plus y squared just equals the square root of x squared plus y squared. Okay, and now we have a result that can also tend to 0 by the squeeze theorem. So you can see that this question, just simply by the fact that I had this sign here, a lot of these limits are just calculated via the pinching or squeeze theorem, same thing. And now because we've shown that this whole limit equals 0, by the definition, it is differentiable at the point 0, 0. So we've proven as required. So let's move on to our next useful rule when it comes to differentiation. That's the chain rule. So it's an extension of the ordinary chain rule for one-dimensional functions, except in this case, what we're going to be getting is this expression here. That says that the derivative of g of f at some point A is equal to the derivative of g evaluated at the point A multiplied by the derivative of f at the point A. Now notice that these will be Jacobian matrices. Okay, so what we're doing is actually multiplying matrices. So when we're evaluating this, it will be a matrix multiplication. Okay, now we just need to keep in mind conditions for this theorem to hold true. Those conditions will be differentiability. Okay, so everything is based on differentiability. We need them to be differentiable in order to apply this property. So now let's move on to an example, or in this case a theorem from MATH2011. It says here that suppose that f is a differentiable function of two variables x and y, so we have f of xy, and then x and y themselves are differentiable functions of two variables s and t. So we get this result here. So that means that f of st, okay, which is the composition of these two functions, okay, has the following partial derivatives. So df ds is equal to this expression. So df ds equals this thing here, and df dt equals this thing here. So you can kind of see it's sort of like the ordinary chain rule, except we need to account for not only this x, but also this y. And then same here, x and y. And these results are just sort of corollaries of the previous theorem. So all of these chain rules, so the following chain rules, can all be derived from this from this theorem. So if you're going to commit one to memory, you should be remembering this chain rule. So now let's apply this in a question. So it says use the chain rule to find dz dr, dz ds, and d squared z by ds dr in terms of all of these partial derivatives if we have the following. Z is a function, well, z equals f of uv, and u equals 2r minus s, and v equals r plus s squared. So let's go ahead and try find dz dr, for example. So using the previous result, you can sort of just apply this. So dz dr, well, that's going to be df du dr plus df dv dr. So you can see that we need to be accounting for the fact that f is a function of uv, so that's why we have df du dr, then df dv, and dv dr. Okay, so now from here, what we can do is just sort of use the fact that we can actually calculate du dr because we have these expressions up here. So these expressions allow us to actually just calculate and compute these derivatives. So we can compute them. So that's just equal to 2, and dv dr just equals 1. And that means that implies that dz dr is equal to 2 df du plus df dv. Okay, so now we can use this basically the exact same idea to find dz ds. There's no difference there. We're just using the chain rule again, and what we'll get is this expression here. So these are our two expressions. Now we're not done because we needed to find d squared f by du dv. So to actually do this one, it's a bit more complicated, so I'll break it down. Let's just get some paper. So what we're going to be doing is actually, so we're trying to find d squared z by, I think it's du dv. So in this case, we're not going to be assuming any sort of continuity because we don't know anything about the function f. So the order will matter. In other words, we can't use the theorem that the second partial derivatives commute, assuming their continuity. So we're going to ignore that. We're going to be considering the order. So the order in this case is this. So we find this derivative first, and then find its partial with respect to u. Now, how do we actually compute this in terms of the chain rule? Well, dz dv can be thought of, as a function of r and t. Okay, so it's a function of r and t. And if it helps, we could say call it maybe f of rt, and that means we're just trying to find df dr, df du. Now remember, df du will be df d. We're trying to find. Sorry, dds. My bad. I've written this down wrong. We're trying to find ds dr and ds, and there's dr here, and it's not. Sorry, it's s and r, not r and t. So that's function of r and s. Okay. So we can think of this as a function of r and s, and then what this becomes is just, that's an s there, du ds plus df dv dv ds. Okay, and now what that's going to be is, well, what exactly is df du? Well, that's the same as d du of dz dr, okay, multiplied by du ds, plus d dv of dz dr times du ds, okay, so that's d squared z over du of, sorry, give me a moment. No, we're trying to find this. Oh, sorry, DSDR. My bad. Sorry. Just give me a moment. DSDR in terms of this. Sorry, in terms of this. So we're trying to find this in terms of that. So that means that we'll just follow this working out. So what happens is we're just sort of expanding it out first. So I think what I forgot to do here, which is my bad, is we have DDS of DZDR. Now we don't actually have an expression for DZDR that we can, well we do, sorry, but we need to use it from the previous part. And that was this expression. Okay, and from here what we can do is then apply these rules. So DDS of DF du plus DDS of DF ds, okay, and V, sorry, and that should give us 2d squared f du squared du ds. So you can kind of think about it as these sort of du's are cancelling out, and that will give us the same expression as we had before. And then from here, what we can do is, I guess from here, what we can do is realize that we can actually find du ds, dv ds, that sort of thing, and substitute it in. What we should get is this big expression here. So if you have any questions, let me know in the chat. But these will all be published. All these solutions will be published online. So now let's move on to our next concept, which is the idea of a gradient. So what a gradient is when we're working with functions from Rn to R, Rn to R. So we're dealing with a function of multiple variables, maps to the real numbers. So in that case, what we're working with is a Jacobian matrix that is actually just a row vector. And then we consider it as a vector. So that is the gradient vector of f. Now, in terms of MATH2011, this can be written fairly straightforward if we're working with a function of two variables. So we're working with f of x, y, for example. Then the gradient of f is just df dx, df dy. Okay? Now, in terms of the actual meaning of a gradient, what is it? Well, it is a vector, so it has direction. So what does that direction mean? Well, it gives you the direction of steepest change at some point. And it is always orthogonal to the tangent plane at that point. Okay? So it is a normal vector to the surface. Okay? So given some surface, the gradient of the surface is always the normal vector to the surface at that point. And that's why we can write the tangent plane in this nice expression here. That's because this is just the point normal form. That's exactly our point normal form, okay, using this as our normal because we know that the gradient will always be orthogonal to a surface. So let's apply that idea in practice. So now the question here is, does the surface here and this sphere touch tangentially? So do they touch tangentially? So to prove this, what we can do is first, well, it's easier if we label these as different surfaces. So I'm going to call that phi1 and phi2. Those are our two surfaces. And this is the same thing as saying phi1 of xyz equals 30. And then phi2 of xyz equals 12. Okay? And now from here, well, how do we actually show they touch tangentially? So we can kind of think about it using a diagram. So given these two surfaces that do touch tangentially, you can see that what we expect is that for the tangent plane at that point, well, they have the exact same tangent plane, right? But that is equivalent to saying that they have parallel normal vectors at that point, okay? So as long as the normal vectors to the two surfaces at that point are parallel, that means that the two tangent planes will also be parallel. And because they coincide at the same point, if the two tangent planes are parallel, that means that they're exact same tangent plane, and therefore they touch tangentially. So all we need to do is show that the normal vectors are parallel. And that's surprisingly easy because remember the normal vectors would be just the gradient of phi 1 evaluated at the point 1, 1, negative 2, and then the gradient vector of phi 2 evaluated at the point 1, 1, negative 2. Okay? So all we need to do is find these gradients and sub some points in. So, well, we can actually find the gradients, and they're not too complicated because, for example, finding this gradient is just a matter of finding its partials with respect to x, with respect to y, and with respect to z. Okay, so we can just calculate them, and they're here. And now all we have to do is substitute points in. So sub the point 1, 1, negative 2 in, and then we get these two normal vectors to the surface. So these are the normal vectors to the surfaces. And you can see that the gradient of phi 1 is actually 3 times the gradient of phi 2. Okay, so we have that 9, that 3, and that negative 21 to negative 7. So that means that these two normal vectors are parallel. And if they're parallel, that means that the two tangent planes are parallel, and because they coincide at the same point, that means that the surface and the sphere do touch tangentially. That's an application of gradients. Now, we'll move on to another application of gradients that's very useful. That is the idea or the notion of a directional derivative. So what we defined earlier were partial derivatives, but we could only find them with respect to the x and y axes. So if I had some curve, I could find the rate of change with respect to x and y, but if I look at some arbitrary direction, I wasn't able to find it. But now we can introduce this new idea of a directional derivative, which is essentially the rate of change of the function in some arbitrary direction with respect to some unit vector u hat. So the actual definition is very similar to what it was for our partial derivatives, except replacing those basis vectors ei with the unit vector u hat. Now, there's a really easy way for us to calculate these directional derivatives, and that is using the gradient. The gradient says that the directional derivative in the direction of u is just equal to the dot product of the gradient at the point A dot with the direction u. So it's important that this is a unit vector, otherwise we're going to get wrong answers. So we need to make sure it's a unit vector, and this needs to be evaluated at A. Okay, so let's apply this in a question and see how we can use it. So given some function and a curve, find the directional derivative of f in the direction of 1, 1 at the point 1, 8. So this is a fairly standard computation question. So let's put it into practice. So the first thing we need to do is find the gradient of f. So that's going to help us because remember our directional derivative expression is in terms of the gradient, so we need to find it. Now calculating the gradient is just remember looking at the partials x and partials y. In this case, if f of xy equals x to the 2/3 plus y to the 2/3, that's just a matter of 2/3 x to the negative 1/3 and then 2/3 y to the negative 1/3. Okay, and that is our gradient. So now what we need to do is find the directional derivative in the direction 1, 1 at the point 1, 8. So that means is that x equals 1, y equals 8. So that means our directional derivative at 1, 8 is just equal to 2/3, and that should be 1/3. Okay, and now we need to just multiply that, or to find the dot product with this u hat, which is in the direction of 1, 1. So we can see that this u hat should just be equal to 1 on root 2, 1 on root 2. So that's in the direction 1, 1, and it's a unit vector. So we need to make sure we divide by root 2 in order for it to be a unit vector. So what that means is that when we actually just calculate the directional derivative, it's just the dot product of these two. It's just the dot product of these two, and what we should get is just 1 on root 2. And that is our directional derivative at the point 1, 8 in the direction 1, 1. So now what we want to do is remember our curve. We had some curve that was defined like this. And what we want to do is find its the magnitude of its derivative. So to find the derivative is just a matter of differentiating each of these individual components with respect to t. That should give us 3 sine squared t cos t minus 3 cos squared t sine t. So now to find the magnitude, okay, remember this is just an ordinary vector, so we can just calculate its magnitude by substituting components into Pythagoras' theorem. Okay. And when we actually compute this, what we should get is this expression here. So what we can actually do is take out a factor of sine squared t, cos squared t, and that leaves us with sine squared t plus cos squared t, which equals 1. Then we take it out of the square root. What we should get is 3 sine t cos t. Now we can ignore absolute value signs, that sort of thing, simply because we're working with t in this particular range. And now in this range, sine and cos are both positive, so we can ignore issues revolving sine for now, like the actual sign, positive or negative. So that's our answer. It's just 3 sine t cos t. Now here we have this question. So for every point on the curve r of t, find the directional derivative of f in the direction tangent to the curve. What does this tell you about the value f on the curve r of t? So what the question is doing, so we'll break it down, is asking us to find the directional derivative of f in the direction tangent to the curve for every point. So that means we want to find the gradient of f evaluated at some point, multiplied, or dot product, with the tangent vector to the curve at that point. So for example, if we have the curve here, what we want to do is, and if we're looking at this point, is find gradient at this point. Oops. So gradient of f, that's a nabla f of a, and then this is our tangent vector. That's our tangent vector. Oops. And what we want to do is find that dot product so we can find the directional derivative in that direction at the point. So to break it down, notice that every point on the curve is r of t. Okay, as t varies, that gives us every point on the curve. So what we want to find is nabla f of r of t. Okay, now what about the tangent vector? Well, we know that r dash of t represents a sort of velocity, which means that the direction of the curve, the tangent direction, will be related to the derivative r dash of t. But remember that we always need to multiply by a unit vector. So we need to multiply or find the dot product with r dash of t divided by its own length in order for us to be finding the dot product with a unit vector. Okay, so now what we want to find is this expression here, or we want to evaluate this expression. So this expression is this. What we can do is use the fact that r of t equals sine cubed t cos cubed t, which means that that's sort of x equals sine cubed t, y equals cos cubed t, and we can sort of just sub it into our expression for nabla f that we calculated earlier, and then find the dot product with this expression. So notice that what we're going to be getting is something like this. 2 over 3 sine t, comma 2 over 3 cos t, dot product with 3 sine t minus, comma 3 cos t, negative 3 cos t. So you can kind of see that these 3 sine t, 3 cos t cancel out. What we get is 2 minus 2 equals 0. So what we got is that the directional derivative is always 0 along the entire curve. It is not dependent on t, which gives us how far along the curve we are. It is always equal to 0. So what does that mean? That is saying that f is always 0, or the gradient of f, sorry, the derivative of f in some direction along the curve. So I'll reword that using a diagram. So as we vary along the curve, for each point along this curve, if we look at the directional derivative along the tangent to the curve, we always get 0. What that indicates is that the curve, or the function, must be constant along the curve. That's because the derivative equals 0 along every point of the curve in every direction that the curve is pointing in, which means that along the curve, what we'd expect is that the function is constant. So we can conclude that f is constant along r, along the curve r. And that is because the directional derivative always equals 0 along the curve. So now what we're going to do is introduce a new idea, which is the Hessian matrix. So working with a function from Rn to R, the Hessian matrix, similar to the Jacobian, is a way of encoding all the information about the partial derivatives, but this time of second order. So you can see the key thing about the Hessian matrix is that along the diagonal what we get are the second derivatives with respect to a certain direction. So we get d squared f by d. See that the variable in question will be changing. So it starts with x1, then x2, all the way up to xn. So now the reason why we introduce this idea is because it's helpful when we're talking about Taylor polynomials. So if we're working with an open function, an open set and a function, what we can do is actually write its Taylor polynomial like this. So the Taylor polynomial is f of a plus the gradient of f, dot product with x minus a. That's the first order Taylor polynomial. Now the second order Taylor polynomial involves our Hessian matrix. Now these expressions are kind of complicated, so we're going to be looking at a simpler example soon, but we'll move on to looking at maxima, minima, and saddle points first. So a stationary point is one where the gradient equals 0 at that point. Now, all of these ideas are sort of extensions. So these ideas are extensions of the single variable calculus case. So we can look at global maxima, that's the largest point on the curve, global minimum, smallest point on the graph. And then local max and local min is when we start dealing with an open set around some point. So, if we look at, just remember from single variable calculus, these two will be our local max and local min. And then these points at the end will be our global max and global min. Now, there's a new idea, however, when we're extending into multiple variables, and that's the idea of a saddle point. So that's a stationary point that is neither a maximum or a minimum. So we'll look soon how to test for that. But before we do that, let's look at critical points. So 3 types of critical points. Those are stationary points, boundary points, and points where the function is not differentiable. Now we know that all the local max min will occur at these critical points. So what we can do is sort of investigate these critical points when we're trying to find max and min. Now, in order to investigate the nature of stationary points, we need to look at positive and negative definite matrices. So an n by n matrix is positive definite if all its eigenvalues are positive. It's positive semi-definite if all of its eigenvalues are non-negative. So it's greater than or equal to 0. And then negative means it's negative definite, and non-positive is negative semi-definite. Now, the reason why we look at that is because that helps us classify our stationary points. So given stationary points, we can classify them as local max, local min by looking at the Hessian matrix. That's why we introduce it. So when the Hessian matrix is positive definite, that means we're working with local min. If it's negative definite, then we're looking at a local max. Now, we can sort of go backwards. If it's local min, then all we know is that it's positive semi-definite. And if it's local max, then all we know is it's negative semi-definite. Now, if the matrix is neither, okay, so it's neither, a positive definite, negative definite, that means we're dealing with saddle point. So where the matrix is sort of not satisfying these properties, that's when we can sort of realize that it's a saddle point and not a local max or a min. Now, another way to quickly test whether a matrix is positive definite, positive semi-definite, that sort of thing, is using Sylvester's criterion. So that means looking at the upper k by k submatrix and the determinant. So if I have a matrix like this, let's say we have all these elements like this, okay? What that means is we look at the determinant of the upper k by k submatrix. So that means looking at this one, and then this one, and then this one, and then the entire thing. Looking at all those determinants. Now, where all the determinants are greater than 0, that means we're dealing with a positive definite matrix. Now, when they're all greater than or equal to 0, then it's positive semi-definite. Now, if they're all less than 0 for odd k and greater than 0 for even k, then we're dealing with negative definite, and kind of similar for negative semi-definite. So this sort of thing you'll just have to commit to memory, but it's helpful for actually determining whether matrices are positive definite or negative definite. Now, going back to the Taylor polynomial, in terms of MATH2011, and even for MATH2111, we can sort of remember these easier expressions for the Taylor expansion. So that means the Taylor sort of expansion for this expression here is given by this big thing. And you can kind of see that when we're dealing with a Taylor expansion, it's very similar to the single variable calculus case, except we introduce this term here that involves the mixed derivative that has a factor of 2 at the front. Now, critical points in terms of MATH2011, so that's very similar to what we did our definition earlier. And yes, so these are very similar definitions. Now, in terms of MATH2011 again, we can look at the second derivative test. So supposing the second order partial derivatives are continuous on a disk, and suppose that they both equal 0, then we can look at this thing called a discriminant. So that is the mixed derivative squared minus the individual second derivatives. And looking at its sign, so that can tell us whether it's a local max or local min. So that's a lot of theory. Let's just jump into a question and apply this. So first of all, find all the stationary points of f. So to find stationary points of f, remember that's points where the gradient equals 0. So what we're going to need to do is find when the gradient equals 0. So the actual gradient itself equals to this. Now what we need is to solve this simultaneously. So that's each of those components in the gradient equaling 0. So in the first one, we can see that y, 2y outside of x plus 2 equals 0. That means we can get y equals 0 or x equals negative 2. And now we can sort of substitute them into the second equation. And that gives us these 3 points. So I'll skip some working out in the interest of time, but again, these slides will be linked online so you can check them for yourself. What we get is these 3 stationary points. So part B of the question is to choose a stationary point of f and classify it. So let's pick negative 5, 0. Now, we need to calculate the Hessian matrix at this point. So the Hessian matrix should just be this. And at that point, we just sub those in. So now we're looking at this as our Hessian matrix. So now we need to find, is this positive, definite, positive, semi-definite, that sort of thing. To do that, we can look at its eigenvalues. So a useful piece of theory here is that the trace of the Hessian matrix will equal the sum of the eigenvalues. So that's trace. And the product of the eigenvalues is equal to the determinant of the Hessian matrix, okay? So by looking at the trace, so remember, if you've forgotten, the trace is just going to be the sum of the diagonal point. So that gives us 4, that's the trace. Now the determinant is going to be, 0 times 4 minus negative 6, negative 6. That actually gives us something that's negative. Okay, so we can see that the trace is positive and the determinant is negative. So you can see that while they add to something positive, they multiply to something negative, okay? Which means it's neither it's neither positive definite or negative definite. That makes negative 5, 0 a saddle point of the curve. So now let's find the Taylor polynomial of order 2 around the point a equals negative 2, 9 on 4. So this Taylor polynomial is going to take this form, okay? So the Taylor polynomial is going to be the point a plus df dx at the point a times x plus 2 plus df dy at a, and then y plus 9 on 4, so minus 9 on 4, plus 1 over 2 factorial outside of d squared f dx squared at a, x plus 2 squared, plus d squared f over dy squared at a with y minus 9 on 4 squared plus 2 times the mixed partial derivative with x plus 2 y minus 9 on 4. So again, in the interest of time, all of these partial derivatives have been calculated, and most of them are equal to 0. And if we combine all of that together, what we should just get is this is our expression for the Taylor polynomial of order 2 at the point. So now let's move on to Lagrange multipliers. So if we're looking at constraints, okay, so let's suppose that we have some function and it's subject to the constraint, for example, y of x equals c. That could be something like x squared plus y squared must equal 1, for example. Now, if we're trying to find the max or min at some point satisfying that constraint, what we can use is the notion of a Lagrange multiplier. We know at this point, what we need is for the gradients to be parallel to one another. So that means that the gradient of f at the point A, so this is our local max, or this is our max or min. Max or min needs to be equal to lambda, some lambda, times phi of a. So remember, phi is our constraint. So that's the gradient of the constraint when we substitute a into that. So that means that we can, sort of apply this in a question and see how it's done. So use the method of Lagrange multipliers to find the max and min values of the function 2x minus 3y plus z on the sphere x squared plus y squared plus z squared equals 14. So we can define this constraint here to be phi of xyz equals x squared plus y squared plus z squared, and that must equal 14. Okay. Furthermore, we can then find the partials. So we can find the gradients. So the gradient should be 2x, 2y, 2z, and then the gradient of f should be 2, -3, 1. Okay. Now we know by the method of Lagrange multipliers that the gradient of f must be equal to some lambda times the gradient of phi at some point where it attains a max or a min. So we can see that as long as x, y, and z are non-zero, then all non-zero, then the constraint never equals 0. So then we can ignore that issue with the Lagrange multiplier. So remember, one of the conditions is that it's non-zero. So now what we're sort of doing is equating, using this to equate components. So then what we should get are these 4 equations. So these are from the Lagrange multiplier. That's from our Lagrange multiplier equation. And this is our constraint again. That should be equals to 14. Okay, so if we solve these simultaneously, so one way of doing it is to say, look at this equation, we get x equals, lambda equals 1 on x. And using that value of lambda, we can plug it into here. If you plug it into here, what we should get is, for example, -3 equals 2y on x. So y equals -3 on 2x, for example. We can do the same in z. And all we have to do is substitute it into this equation. Okay, all we need to do is substitute it into this equation. And what we can do is then find the value of x. So if we actually sub it in, what we should get is, x squared plus 3 on 2 x squared plus, this should be 1/2 x squared equals 14. That will give us x squared equals 4. So we get 2 possible values for x. So that gives us x equals 2 or x equals -2. Okay, so now actually using these values and then finding corresponding y and z, what we get is 2 possible points, candidate points. So these are candidate points for the max and min. So now we just need to substitute them in to test them. So sub them into the original function f, and what we should get is that this point up here gives us our max, and that point gives us our minimum. Okay, so I'm expecting that will run a bit over time, so just bear with me here. Again, this is all going to be recorded so we can watch online later if you're busy. Now we're going to be moving on to the inverse function theorem. Now what the inverse function theorem says is that with a continuously differentiable function on an open set, okay, as long as the derivative is an invertible matrix, okay, then f is invertible on an open set containing A. Okay, so on that open set containing A, okay, let's say this is the open set here, okay, when we find the matrix and we see that it's invertible around the open set, then we can say that the function is invertible, and furthermore, we can use its the inverse matrix as the derivative of the inverse function, okay? And that allows us to sort of find the best affine approximation to the inverse function at that point. Okay, so this is an extension of the ordinary inverse function theorem for real-to-real in multiple variables. So we're sort of just using invertible matrices instead. So specifically, if we're looking at the Jacobian matrix, then we can say that in the neighborhood of a point, okay, so it's important that it's not sort of the whole area, it's just in the sort of open set around the point, then we can say that the Jacobian matrix of the inverse is the inverse matrix of the original Jacobian. Okay, so applying this in a question, given this function here, find its Jacobian matrix. So its Jacobian matrix should just be, remember, it's going to be df1 dx, df2, sorry, df1 dy, df2 dx, df2 dy, and that should give us this here. So using the inverse function theorem, we know that this, well, I guess without using it, we can see that the determinant at x equals 0, y equals 0, we can see that the determinant is non-zero. Because remember, if the determinant is 0, then it's non-invertible. So we can see that det, or the Jacobian matrix at that point, is non-zero, which means that it is actually invertible. If it's invertible, that means that there is a differentiable inverse around 0, 0 by the inverse function theorem, okay, in the neighborhood of that point 0, 0. So we're going to move on to the next topic, integration. And we're going to be moving through this fairly quickly in the sake of time. So quickly looking at the definitions, remember that everything is defined using Riemann sums. So this is our idea of the lower and upper Riemann sums on a rectangle. Okay. Now, when it comes to Riemann integration, as long as there exists, some number between the lower and upper Riemann sum that's unique for every single possible partition, then we can say that the function is Riemann integral on R. Furthermore, the Riemann integral is equal to that number that's sandwiched between the two lower and upper Riemann sums. Okay. Now we can denote it like this. This is our Riemann integral. So how do we actually calculate that? Well, first of all, we need to consider the notion of regions. So a region is y simple if there exist continuous functions such that, this following is true. So the easiest way to think about this is just using, a diagram. We can see that we need x to be bounded from a to b, okay? And we need y to be bounded by two functions. So, for example, this would be perfectly fine because we can see that the y is bounded by two functions. Specifically, that's phi1, that's phi2. So really, when it comes to x simple, y simple regions, it's about being bounded by just continuous functions. Now, in terms of x simple regions, it's going to be looking a bit like this. So instead of looking at the x, we're going to be looking at y, and then we need there to be some functions that bound it like that, for example. Okay. And as long as it's x simple or y simple, we can call it elementary. Now we can just have we have some properties of the Riemann integral. These are sort of the properties that we expect. And now we're moving on to Fubini's theorem. Fubini's theorem is essentially the idea that as long as these conditions hold, then we can reverse the order of integration. Now let's apply that here. So before I go on, we just need a bit more theory, and that is actually calculating irradiated integrals. So that's calculating our double integrals. How do we actually do it? Well, it's a matter of looking at our bounds. We need to be careful with the bounds. So suppose we're integrating over a y simple region bounded by these two x equals a, x equals b, y equals phi1 x, y equals phi2 x. Well, the integral is going to be equal to this expression. So notice that we integrate first with respect to x and then with respect to y. And that allows us to actually, well, I think this should be the other way around. So that should be, we first integrate with respect to y, then integrate with respect to x. So we can kind of see like we're grouping these two together. So the dx is associated with the AB bounds and the dy is associated with the phi1x, phi2 bounds. So now let's actually calculate a double integral to see how it's done. Well, this question here says, first sketch the region of integration for the following integral, and then evaluate it first by changing the order of integration. So notice that right now, in its current form, I can't actually integrate anything because this function is not integrable, I guess, using elementary functions with respect to x. So we actually going to have to change the order of integration. How do we do that? Well, we need to actually look at what region we're integrating over. So the region that we're integrating over is Well, let's investigate. So we can see that the y is associated with 0 and 1. That means that we're integrating from y equals 0 to y equals 1. Okay, so we need to put that here. Now in terms of the x we are integrating from the curve y squared up to 1. So x equals y squared is this function here. Let's draw it in. And we're integrating from y squared to 1. That means we're going from x equals y squared to x equals 1. That will actually give us this lower area here, okay? Because we can kind of think about it as we first need to like let me just get my color here. We're like between. We need to be between the curve y squared and the curve x equals y squared and the curve x equals 1. Okay. So that's our region of integration. Well, how do we express this in another way? So what we need to do is express this instead of in terms of y, in terms of x instead. So we can see that we're integrating from x equals 0 to x equals 1, okay? And that our lower bound can be 0 and our upper bound can be the curve root x. Why? Because if x equals y squared, y equals root x, okay? So that means that we're going from 0 up to y equals root x. Okay, and that gives us the exact same region, and that means the function is the same inside, because that didn't affect anything, except now we can reverse the order of integration. So we can actually calculate the integral. Well, notice that this integral here with respect to y is just equal to that. Substituting in our bounds, what we should get, that dy should be gone. What we should get now is this, and we can just integrate it, it should just be e minus 1. So now moving on to Leibniz rule. So Leibniz rule is a way of sort of looking at these expressions like this. So if we have the derivative of some integral, or in other words, if we say define some function in terms of an integral, and we want to find its derivative, well, we can use Leibniz rule. This is also known as differentiation under the integral sign. So as long as we're dealing with continuous functions and uniformly continuous partials, then we can move the differentiation under the integral sign, and that's in terms of uniformly continuous. That is just a continuous function on a compact set. So now looking at Leibniz rule of variable limits, this sort of expression comes from the chain rule. Fairly straightforward expression. Again, that's something you'll have to commit to memory. So I'm just gonna skip over this question. So this question is actually a direct application of Leibniz's rule, and you can see that has variable limits. So what we're going to be using is just this formula, okay? But again, in the interest of time, I'll be skipping over it. However, we have the solutions on the slides here, and also the slides will be uploaded to the website solutions. Also, you can ask questions in the Discord server if you need anything. So we'll be moving on to this question. So from 2018, given that this particular integral equals this, so it's pi on a e to the negative 3a, use Leibniz's rule to find this integral. So you can see that there are slight differences. You can see that what we have here is x squared plus 4 all squared versus x squared plus a squared. We can also see there's no a, that a is equal to 2 of 4 in this case, right? So what we need to do is use Leibniz's rule to sort of manipulate this integral. So in other words, we're trying to turn this integral, the one we know, so we know this integral, into the integral we don't know. How are we going to do this? Well, considering that we have this integral expression in terms of some variable a, so we know that this is in terms of some variable a, we can perhaps express this in terms as a function of a, okay? And we can use Leibniz's rule. Specifically, we can kind of see that these two sort of look like derivatives of one another, because in general the derivative of like 1 on x equals negative 1 on x squared. So ignoring sign, you can see that this squared part may come about through differentiation. Okay, so it's something that we kind of just have to try. Now, just trying it, we can see that if we apply the derivative, we know that this is our expression for the integral itself, and that is also a function of a, so we can differentiate it with respect to a. What we should get is, once we move the integral, so the differentiation under the integral sign, we'll get this, and this is also just our normal single variable derivative. Now, you can see that when we differentiate this with respect to a, we get sort of what we need. We can see that that squared comes out. We just have this constant out the front. Now, it is a constant because we're differentiating with respect to x. So integrating with respect to x. Now, from here, we sort of just need to rearrange. And by rearranging and we're subbing x equals 2, then we just get what we need. Okay. Now, moving on to the next idea, that is change of variables. So change of variables is sort of an idea extending substitution, integration by substitution into the multiple integral case. Now, how we do it is, what we need to do is, well, first of all, find some function f that can be a substitution, our change of variables, and then we need to make sure that we multiply by the determinant of the Jacobian at f. So the reason why we need to multiply this by this determinant is so that the way area scale remains the same under the change of variables. So the easiest way to understand what's going on with this theorem is just to apply it in a question. So let's look at this question. So we have the double integral over some bounded area of x squared dx dy. So it tells us that the area is the bounded portion of the first quadrant lying between two hyperbolas and two straight lines. So through Desmos, we can see that this red area is the one we're interested in. So now what we need to do is, well, find the integral of the function over this region. Now it's going to be difficult because you can see that we have these expressions in terms of x and y. This is not as straightforward as our original x simple and y simple case. So what we need to do is think about new functions that we can sort of change our variables to in order to make it easier. So I'll word that again. In other words, if this was a function u, clearly u is just bounded by half and 2, which is easy to work with. And we could also figure out what's going on in this case, and it shouldn't be too complicated. So what I mean is, what we're going to do is define u equals xy and v equals y. So that's our new function v. So now, if that's the case, then you can see that we have u equals xy, v equals y. Well, we also know that that means that u equals xv. Okay, so x equals u on v, and then y equals v. Okay, so we have these two expressions for x and y in terms of u and v. Okay, so now what this means is we're integrating over this instead. We're going to be integrating over u bounded between 2.5. And now what about v? Well, you can see that it's x on 2. We know that x equals u on v, so that's just 2u on v less than v, which is less than 2x, which is just, well, in this case, 4u on v. So that's, I believe, sorry, it should be this expression. So now we have these two, and what that means is, well, we can just sort of rearrange this one a bit so it's a bit easier to work with. We get this expression. And now these are exactly the same as normal integration thing, regions of integration that we did previously. Now the only thing we haven't accounted for yet is this determinant part, So we need to find the Jacobian of f. Well, what exactly is f? Well, f is this. F is x is a function of uv, and y is a function of uv. Okay, so that means the Jacobian of f will look like this. And well, for example, finding dx du is not too complicated because we know that x equals u on v. So dx du just equals 1 on v. And dx dv equals, well, negative 1 on v squared. Okay, negative u on v squared. Okay, and all of that gives us a determinant of 1 on v. So that means that to actually calculate the integral, it just becomes this. So it becomes this. So you can see that we have changed our variables. That means we've changed our bounds, and we've also introduced this 1 on v when it comes to changing it to dv du. Okay, and now in terms of this integral, it's something that we've calculated before, and it's just a matter of, this integral is with respect to v. U as a constant, treat u as a constant, should be fine. Evaluate the bounds of this, and then evaluate integral again, and we should just get 45 over 32. Now, that does conclude the end of the first part of the course. Now, we have released a revision sheet for Math2011. So that is a sheet of all the theorems and results that are useful. So I'll be on our website. It's going to also be linked somewhere on the slides. The slides will go on the website. It's going to be linked somewhere on Facebook or this YouTube description. So just keep posted for that. But it's already uploaded. So if you check our website now, you'll be able to check it. But thank you very much for attending. Thank you a lot to Jason for presenting the previous part, and I think the next part will be on Friday, so keep posted for that. So those are the last two parts of the course, so Fourier series and vector calculus. Again, thank you for coming, and good luck for your exams.